Hi, we want to present you the project we did on implicit neural representation with GNN and contrastive learning. Without further explanations, let's dive in. First, let's explain what is implicit neural representation, or INR. INR is a different way to represent data using a continuous function from coordinate space to some feature of the coordinates. The function is approximated by a neural network, and the data can be basically anything: images, point clouds, audio, time series, and more. INR has many benefits over fixed representation. For example, it is easier to scale the data, and it's more effective in representing complex data structures like point cloud. Recently, it's been suggested that INR can serve as an input to some other neural network, instead of the classical representation input. Since INR is a neural network, it is obvious to represent it as a graph. Let's see how this can be done. INR consists of matrices of weights and biases, which stores the parameters of the network. One simple way to represent them in a graph, that was suggested by Kofinas et al., is to store the biases as node features and the weights as edge features. This way, the adjacency matrix is a block matrix corresponding to all the INR layers. One thing to remember is that not all GNNs are using edge features as learnable parameters. This is why we use the architecture called relational transformer, which adds the edges to the attention mechanism while keeping the complexity squared in the number of nodes. Now, let's think on the invariants or symmetries of this parameters domain. Obviously, it is invariant to permutation, noise addition, and scaling. Rotation and translation are more subtle and are symmetries of INR specifically. Sparsification is when we take only the strongest nodes in the graph. Together with dropout, we expect that this would be symmetries in a downstream task. This leads us to the idea of self-supervised learning in the parameter space. If successful, self-supervised learning would be a powerful tool for representation learning in the weight space and can be used for multimodal transfer learning, for example. We used contrastive learning with SimSiam framework and performed experiments with different transformation on MNIST INR dataset. These are the results of the experiments. The left panel shows the loss and the feature standard deviation of the self-supervised training. The standard deviation was suggested by Chen as a measure to convergence to a non-trivial solution. We can see that all the experiments converge to a non-trivial solution, and the brown curve converged to higher loss compared to the others. This curve represents an experiment where instead of taking a transformed version of the same INR, we took different INRs representing the same label as pair. The right panel shows the downstream results on MNIST classification task using INR. We compare the SSL experiment to a baseline, the blue curve, with no self-supervised pre-training. We see that except the different pairs experiment, all the experiments converge more or less to the same accuracy, when some did it faster than the baseline and others slower. For a closer look, let's look at the accuracy table. Here, we see that also very close, none of the experiments outperform the baseline. Among the SSL experiments, the best one were those where we use sparsification. This is important since the size of the graph poses strong limitations on the possible network that can be represented as INR. Using sparse representation enables large INRs almost without loss of information. The inevitable question is, why the results didn't improve with SSL? To try and answer this question, let's look at the attention weights. Here we see the attention weights of an example of correctly classified samples with and without SSL phase. We see a clear difference between the weight structure. Without SSL, in the upper panels, we see that the attention of nodes is mainly to nodes within the same INR layer, and the attention structure within each layer are similar. In other words, the network preserves the structure of the INR. Without SSL, we see a different story. The attention is mainly between nodes from one layer to the other, and the attention within the first layer are much weaker compared to the attentions within the second layer. To better see this phenomena, we will look at more samples. This graph shows the mean attention weights per node for a subsample of 2000 correctly classified and misclassified examples. The difference seen before is even more clear now. Without SSL, we see a monotonic increase in the attention power from the first to the last node. This is a representation of hierarchical learning as happening in the INR itself. With SSL, the monotonicity disappeared and most of the attention power is concentrated in a specific layer. Our conclusion is that using self-supervised learning breaks the inherent structure of the INR with long-range and cross-layer attentions. Since we saw this pattern in different transformations, we conclude that this is not a result of a specific transformation, but of the process itself. To overcome this and make self-supervised learning effective, some changes to the model or to the learning process needs to be done. One such example is local positional encoding. Another idea is to force hierarchical learning by using subgraphs corresponding to different INR layers. Now let's move to a different experiment with different dataset.
Bedlam dataset is a dataset of RGB videos with ground truth 3D bodies in SMPLX format. It includes a diversity of body shapes, motions, skin tones, hair and clothing. In our work, we use this dataset for 2 experiments and compare the results. For the first experiment, we created Bedlam HMR dataset. It is a dataset of modified HMR head modules trained on 1 image each. For that purpose, we took 2 out of 26 Bedlam image subsets. One subset of thin people images with low BMI shapes and one subset of fat people images, high BMI shapes. For this dataset creation, we used modified version of the regression part of HMR. The changes we made are: we reduced hidden layer size by factor of 8. We also reduced the regression iterations count from 3 to 1 and actually removed the part for this blue round arrow on the top picture. And finally, we increased beta loss weight and shape loss weight by factor of 10. We used the pre-trained feature extraction model provided by Bedlam code. So the dataset consists of only the HMR regression parts pre-trained for 100 epochs. The bottom picture is an example of training results of a dataset item.
To create an INRs of the Bedlam dataset, we used Siren, a network that was suggested by Sitzman with periodic activation function. This network converged faster than usual networks and better preserves the information. This way we were able to quickly create a dataset of 2000 Bedlam INRs, one for each image. Now we have 2 different neural network representations of the same data, one using regression network and one using implicit neural representation. To compare those representations, we performed a BMI binary classification task. For each image, the network simply needs to classify it to high or low, where high means that all the people in the image has high BMI and low means the opposite. Since there is no mixture of high and low within each image, this is a relatively simple task. Here, we see the validation results of INR and HMR representations on the task. We see that INR easily outperforms HMR. It converts quickly to almost 100% accuracy, while HMR didn't manage to learn anything for 20 epochs. This suggests that the information stored in INR is much more effective as data input compared to regular network parameters. Now, let's conclude. In this work, we extended graph representation of INR with contrastive approach. We noticed that it achieves comparable results but do not improve the results. By attention analysis, we concluded that this is related to long-range interactions, which, while useful by themselves, break the inherent structure of the INR network. We suggested some ways to improve the framework in that manner. We also noted that sparsification always improves the performance, which suggests that INR representation can be sparse. In a different experiment, we compared the INR representation with feature representation learned by regular network, and showed that INR representation is much more effective to learn in the parameter space. We think that INR is a really cool idea and holds a great promise for non-trivial datasets, and really enjoyed working on it. Thank you.